Let's now talk about asymptotic notations. Asymptotic notations are the mathematical notations to represent order of growth of any mathematical function. There are mainly three popular asymptotic notations: big O, which represents exact or upper bound on order of growth; then theta, which represents exact order of growth; then omega, that represents exact or lower bound. So why do we need exact or upper? Why do we need exact or lower? Say if I have a function c1n plus c2, I can ignore the lower order terms, right? I can ignore the constant. I can say that order of growth is n, right? And if I take another example, say if I have c1 n square plus c2 log n plus c3, right? I can always tell you the exact order of growth. I can ignore the lower order term, I can ignore the lower order term, ignore the constant. I can say order of growth is n square, right? So I can always use theta notation, or I can always tell the exact order of growth. Why do we need big O notation, which is exact or upper, or omega notation, which is exact or lower? Let's understand it with an example. Say this is a linear search code, and this example is similar to the examples that we discussed in the previous video, where we talked about in certain cases we were taking constant time, in certain cases we were having linear time, when we talked about that get sum function, modified that get sum function. So the same thing happens here. If you talk about linear search, and say if you have this array, and say if you are searching for an element x, right? This function, what it does, it takes an array, size of the array, and an element to be searched in the array, traverses through the array. As soon as it finds a match, it returns the index of that match, and if it does not find any match after traversing the whole array, it returns -1. So say you are searching for 10 only. So what will happen in this case? It will find the 10 at the first place, it will return immediately. So it's taking only constant time when the element is present at the first location, and when the element is not present at all, then it's going to traverse through the whole array, right? It's going to come out of the loop, it's going to return -1. For example, if you search something like 75, right, it's going to traverse till this point, and then it's going to realize element is not present, it's going to return -1. So in the worst case, it's going to do linear time. Now if I want to say anything about order of growth of this function, I'll have to say something like this. Say in the best case, it takes constant time. In the worst case, it takes linear time. And if I just want to say this thing in one line, or say I don't want to evaluate the best case, right, evaluate other cases, I just evaluate the worst case. And what I say is, I say this algorithm takes big O of n time, right? Big O of n means it's either linear or less than linear. As I said, it represents exact or upper bound. So if you have a function which is c1n plus c2, you can write it as big O of n. Mathematically, you can write it as big O of n square also, right? Because any upper order growth can also be written in big O notation, right? You can write anything higher than n, right? Not less than n. You can write either n in big O notation, or you can write anything higher than n. You can write n log n, n cube, n4, or anything. So the point is, if I say that this algorithm is big O of n, what it means is, it means either it takes linear time or takes less than linear time. So with big O notation, I can talk about this time taken of this algorithm in one line. We'll be discussing big O notation, theta notation, omega notations in separate videos in detail. The idea here is to introduce these three notations. Big O means exact or upper. For this algorithm, I can say it's big O of n. Theta means exact. For this algorithm, I can't represent the time complexity using theta notation in one line. If I use theta notation, then I'll say this algorithm takes theta n in the worst case, right? That's what I can say about this algorithm, because in the worst case, when an element is not present, it has to traverse after the till the end, and then it has to realize that element is not present, right? So in the worst case, it's theta n, right? I'll have to use the word worst case when I'm using theta notation. Omega notation is opposite of big O notation. It represents lower bound or exact bound. So if we talk about this function, see, in the best case, it's going to take constant time. And constants, when we talk about big O and theta, theta 1 represents constant, and big O 1 also represents constant. When you write theta 1 and big O 1, we mean that constant, right? We'll discuss these things, these notations in detail when we talk about big O and theta. But big O 1, theta 1 means constant. With any notation that you write 1, it means a constant value. See, omega 1, since it's exact or lower, what it means is, it's either constant or any value higher than constant. So big omega 1 or omega 1, it represents a constant value or any value higher than constant. So if you have a function c1n plus c2, you can write this either as omega of n, that will be like exact bound, because exact bound is there in both big O and omega. So I can write it as omega of 1, right? Omega of n. This is how we write the omega notation, and I can also write it as omega of 1. This is also mathematically fine, because omega means lower as well. So what I do is, I write the time complexity of this algorithm is omega 1, right? And when I say omega 1, it means either constant or any value higher than constant, which means this covers all the cases. So we are saying it takes constant time or higher than constant. That's what we mean by omega 1 or constant, right? And when we say big O of n, that means it takes either linear time or less than linear time. Here what are we saying? It takes either constant time or higher than constant time. But which one you would prefer? See, as we have discussed in the best case, average case and worst case, we are most of the time interested in an upper bound, right? That's why omega notation is not used much. You would rarely see omega notation in analysis of algorithms. Most of the time you would be seeing big O notation and theta notation, because theta notation gives you an exact bound and big O notation gives you an upper bound, and you're most of the time interested in either knowing the exact bound or knowing the upper bound.